So welcome to lecture 15 of MCS 507, a course on mathematical, statistical and scientific software. So today we will introduce Cython. So Python is a very flexible scripting language, having the disadvantage of being therefore rather slow, but we can make the code that is defined by Python scripts run a lot faster. We've seen in this course already two different methods to do that. So the first method is to apply vectorization. We've done this in lecture 4. The other way is to call external libraries. And the third way is to generate code. Last week we introduced PyOpenCL and PyCUDA, and these two packages generated efficient code. So today we are running Cython. So Cython is a tool to generate efficient C code. So there are three parts in this lecture. So we start with a hello world, generating our first C program. Then I follow the documentation. I managed to reproduce a numerical integration example, where we go step by step through the ways to make an existing Python script run much more efficiently. When we introduced vectorization, I left the game of life as an exercise, and you can make the game of life a lot faster also with vectorization, but you have to change the logic of the program, and that exercise in lecture 4 is not easy. So Cython has the advantage of keeping the original structure. So this lecture will end with mentioning of numba, which is another tool that works together with Cython to generate define compiled code. Okay, so let's get started then. So what is Cython? So Cython is based on Python, so you can very much stay within the scripting world. But what gets added are type declarations. So if you add type declarations, also if most Python implementations are based on C, one often speaks of CPython. You can also directly call the C libraries. That also makes it a lot faster. So there are two papers left cited here. I'm following these papers, so these are also recommended reading. In the numerical integration example, I'm following rather closely one of these papers. So I installed it very recently also on a Windows computer. The current version is 0.29.27. And everything, I created this lecture, last time I used it was 3 years ago. Everything still works, so it's fairly stable. Okay, how does Python work again? It's a scripting language that interprets the code. It makes it therefore to be very flexible. The typing mechanism is dynamic, so during runtime Python will figure out what is the type. So that makes it very flexible, but also rather slow. Cython tries to combine the best of both worlds. It will compile the code. So we will generate C code, and if it's compiled with the full optimization flags, it will run just as fast as machine code, just as you would have written it immediately in C. So what Cython does allows you to do is to generate code and also to stay very close to the original logic. So without having to completely rewrite the code, as you may be forced in doing when you apply vectorization. Okay, we have seen already the extension modules, and so we are also here now using the tools that Python provides to build these extension modules. Okay, so Cython code has the extension pyx. So here is our first hello world, or hello with a parameter. So it will be able to, when executed, give you a personalized greeting. So we will be using Python 3. I'm not sure if Python 2 is still under support. But I started using this when it was still in Python 2 stage. So here is the setup. So the previous code on the previous slide had the extension pyx. So we will build an extension module. That is what this setup defines. The setup module will be compiled. So it will define a new module that we can import into a Python session. Here is how we do this. So we run the setup, and the build extension module will be running in place. So here you see part of the output. It makes a shared object or a DLL file on Windows, or the ylib on Mac. So this works on many platforms. It may be, so the interesting thing is also that we are running a Python script. So it may be useful also, once you completely want to transition into the C world, to look at these outputs and then capture the outputs into a makefile, which might be useful if you want to keep the C code as a module independently. How do we run this? Well, we can run this also in Python. So here is an interactive Python session. The say hello now is available in the module called hello. So the module hello exports the function say hello, and in a Python session we import the say hello function from the hello module. So it works just like regular Python. So we didn't look at the C code. So in some sense, if you want to know how it looks like, feel free to do that, but it's in general a bad practice to start then modifying the generated code. So you better stay in the Cython world. Okay, so from the pyx code, you can actually generate with Cython. So Cython is a compiler that takes Python input and generates then C code that can be compiled. So what we did before actually consisted in calling the Cython compiler, calling the C compiler, and then doing the linking into the shared object. So Cython looked perhaps rather technical, but it's less technical than what we did before with the making of the shared objects, where we needed really to start from a C program and then adding to that C program the code that defined the extension module. Here actually we can still stay in the Python world. So we can look at C code, but we don't need to. Here is to give an impression what happened on my installation. So if you want to make the creation of the extension module, so this will create the extension module, the .co file on a Windows, on Unix machine that was using the Conda distribution. So a makefile is, if you have to, feel free to, but the makefile is very much restricted, is very specific to an installation, to a very particular way on a particular architecture. So that will only run on a particular machine on a Linux computer that has those locations for the include files. So that's not recommended practice. So it's recommended to work with the setup. Okay, now let's go through an example that I copied from the SciPy proceedings papers. Let's take a computationally intensive computation, the approximation of pi again, with the composite trapezoidal rule. So here is the formula that will be executed. So in Python, it just takes a very simple script to do. If you have taken a numerical analysis course, then be warned that this is a very bad way to work. So there are much better ways to, approximate pi, but much better ways to do the evaluation of the integrals as we do here now. But we need a computationally intensive computation that will take 100 million calls to the square root. So it does a summation, but it is mainly the square root function calls that are troublesome. All right. It could actually be worse. So we need the square root in the function circle. And if we really want inefficient code, we could do the import in the function circle that we are going to call 100 million times. So that would import the module 100 million times. So again, this lecture is also a little bit about writing good Python scripts. So here this is a case where you import a function from a module. So we've seen that in Python you can write math.sqrt, but that will cause Python to look up the math module and from that the square root function. So here we do this on top. We set from math import sqrt. So this is done then only once, this import. Okay. Then the rest of the code is the running of the circle function in the composite trapezoidal rule in an explicit loop. So as you may, well, it could still be worse also here. We do not make a list comprehension where we're going to make a list with the 100 million values in there. So again, it's not bad coding practice from a Python perspective. All right, so this will be our baseline. It is from a Python perspective a reasonable baseline. From a numerical analysis perspective, it is not. So be forewarned here, but it's a good experiment. So here is how it runs. And when I ran this on a MacBook Pro, it took about half a minute to get this approximation for pi. Okay, fine. How can we improve this? Well, we can, when we now define the first improvement, we add types. So our function will be working on doubles. So we add the C types, doubles. So for the arguments, the input argument x is a double. The argument for the integers is also, for the integral for pi, is the number of function evaluations we are going to do. It's the number of function evaluations plus 1. Okay, and then we have local variables. So our loop counter, I, is an integer, is a C integer. And also the step size and the radius, they are doubles. So we have removed the dynamic typing. So we are using static typing on all the variables that we see. So that's our first improvement. How do we build it? Well, this will become a little bit repetitive, but we've done this already with the hello. So we will build an extension module. So compile this code with Python setup. Notice here the optimization flag. So the goal of Cython is to build efficient code. So the -03 means full optimization. Alright, so once we have it, we will apply it. So we need another script where we import now the extension module that we have defined. So the previous setup step created an extension module. The timing is done in this script. So we call the approximation. So the code is self-contained. Here is very short. Okay, so remember we had almost half a minute, and with these type declarations, which does not change anything from the logic, we actually have quite a faster run. So from almost half a minute, it goes to less than 6 seconds. So almost 5 times speed up. All right, we can still do better. So the functions that we call are the return doubles. So we want to we want to add the type information from the functions. So this is now very much how you would define a function in C, where you have the return type that comes before the function, and we have the type of the argument. Okay, so we have some other naming now. And when we add this type information for the square root, where we run the definition of the return type, we get down to 2.7 seconds. So the static typing, going from dynamic typing to static typing, has given us a tenfold speed up, which is not bad. Little work, great benefit. And now comes the last optimization. So we are the main bottleneck here is to call the square root 100 million times. We can directly call the C math library. So this is calling an external function. And since we are working with C Python, so this is automatic. It doesn't need to define an extension module. So it will be building automatically the extension module. So you can kind of see what is the idea, what actually Cython does. We know how to make extension modules. So in some sense, we could already have done this. So we could already have called external functions, but then it requires us to wrap. Cython Cython makes it convenient for us to do this wrapping. All right, so now it gets really fast. So you see it drops below 2 seconds, but below a second. So we are now thinking almost in milliseconds, 222 milliseconds. So more than another speed up of a 10. And compared with our original baseline, we have a speed up of 126. So we have not left Python. So we're still in the Python world, but we are more and more thinking like a C programmer. Okay, so how would a C programmer now write this? So here is the native C code. So we have the double, the two functions, how they are declared. We have to declare the types of all the variables that we are running. And we have the same logic. In a way, one can argue that from a purist perspective, this looks also very clean. C is not a bad language after all. So then we have the main function when we do the timing. So we run this also for 100 million function evaluations. We compile it with the full optimization flag, and you see that the native code is actually 2 milliseconds slower. But I mean that is just a fluke from the timing. So I do not expect the timings to be so accurate that they are up to the millisecond. So, but the main conclusion is that the final Cython code is actually just as fast as the native C code. Fine, I mean, this is now a very simple application. We haven't really done much with more elaborate types. So let's see how it now works with data structures. So working with arrays in C, we've encountered that very briefly with the matrix-matrix multiplication of last lecture. That was kind of cumbersome, so we rather would not do this. Let's see how we can work with numpy arrays a little bit more efficiently. Okay, so numpy arrays are very flexible. What we can do with Cython is that we can access these numpy arrays very, very fast. There are requirements for it. So the arrays themselves must be fixed at compile time. So you will not have fast access if the arrays are dynamically being built during the runtime of the program. Also, one needs to be careful with the indexing. So size underscore t is actually the type where one accesses, that one typically uses for indexing. In lecture 4, we encountered the game of John Conway, and that game runs through the matrix all the time. So, as an exercise in lecture 4, the vectorization will be effective, but it will require some thinking. Um, and then also the correctness might not be that obvious. So that's then the additional problem. Okay, so what we will accomplish is that we will have a faster running game with the same logic. So here is the game of Conway again. So we have a rectangular grid of cells with very simple rules. So the game kind of simulates or has a bacterial growth. So we have elementary life forms. The forms arise if they have three live neighbors. So the cells is actually a cells of bits on or off. The cells either can then also die either by loneliness or by overpopulation. Too many neighbors or too few neighbors. So here is how a screenshot runs, but let me try to do this with a live animation. See how this runs. So here you see the running. And it is a very interesting game. So you see already some blinkers there, but the blinkers are also sometimes destroyed by sliders. So there are slider patterns that traverse this animation. The animation, by the way, is made by Matplotlib. Okay, I let it run for a while. I think it does 1000 steps, and it should become obvious. In a minute, I will run the better game. That the better game will run twice as fast. So we are nearly halfway. And this is, by the way, also a computationally intensive work. I hear the fan of my computer. The computer is working at this time. So if you have to study this, and there is a community that studies these patterns, and there are also much better programs available for this. So if you have to study this, looking for very nice patterns, then you will have benefit of having a better simulation. Okay, so this took about 2 minutes, I guess. So let me run now the better game. And I think it should be obvious that this is running a lot faster. I will be getting a lot closer to the middle of the game. So you see the patterns appearing. This is, by the way, still a very small grid, 200 by 200. But you see the animation is almost over, so I'm at step number 900 almost. You just passed it. Okay, so that was the animation. Let's talk about the way to optimize this. The point is that it illustrates the use of numpy arrays and then much faster access. We will do this. So the animation here is done without visualization, just running it. So, and this will do the pure timing. So there are two phases. So what is so there is the update of the matrix, and then there's also the cost of the animation running. So the total speed up in what we care, our visualization, will be about twice, but the optimization of the update will be a lot more. Here is the setup. Um, so this is running the game of life without the animation. We take a random matrix, deciding already how many cells are alive. So here 20% of all cells, so we have 200 by 200 elements. So this is about 40,000, or this is 40,000 elements. 20% of those are initially alive, but then the game starts running with the update. So we each time in every run we update the cells that are alive. Okay, so how do we make this better? So we count the number of live neighbors. So in some sense, I should have demonstrated also the original code. Um, so um, perhaps it might be possible to do this in this window script now. Um, if I do this with Notepad. So this is the run game better. So this is the input code, and I don't know if that is visible. That is not visible. So I'm improvising here, which is terrible. Okay, so there is another way for me to do this. I can use more on the input. So here we go. It starts with the, and now I can indeed scale this up. Very good. Although it's still not optimal, but there we go. So we have the code. So I can scroll this through this very well. So the code is rather elaborate, but you can see that the logic of the rules actually remains. So we check for the number of neighbors. What So I want to probably point at the rule first. So we have to be careful. So this is also a very good exercise in indexing. So you have to be careful not to, if you look to your left, you have to be careful not to go out of the array. So that's why there is this guard there. So we count the number of neighbors to the left. So this is a Boolean matrix. So we go to the left first, and then we go up and down. Here, taking care that we don't run off. So we count the number of live neighbors. It's important that for every cell, so here we are on this matrix alive, and we have two indices, I and j. So we have to decide what happens to the cell at position row I, column j. So we're working in a two-dimensional numpy array. So this is really using the basic data type. We are therefore being sure that all the entries are being accessed in consecutive order. I think it depends on whether we go row-wise or column-wise. So let us scroll through. So we count more. And then the neighbors returns the number of live neighbors. Let's scroll more through the code. So here we update. So based on the count, we make a new matrix. So on the update, so here we have the number of neighbors. So the number of neighbors is the nbn variable. We make a new matrix of the same shape and we return this new matrix. So there is, after all, quite so doing the update. So if the cell is alive, we have then to decide whether the cell remains alive. So if it can die of loneliness if it has only one or no living neighbors, or it can also die because it has too many neighbors, more than 3 neighbors. So that is the setting to 0 here. So you see the logic works just like you would write it down. So as a Python programmer, we can verify immediately the correctness. So the number of neighbors, that was a little bit tedious to compute. That's in a separate function. And then we have the update itself that returns a new matrix. All right, so let me go back to the slides now. Move this out of the way. So the main important thing is here that the original Python code can very much the same. So what needs to happen are the declarations. So we have the count that is now also a typed variable, and we have the using of the numpy array. Also here in the update, so we have to add the typing from numpy. But we don't have to allocate anything or even deallocate. So in C, we would need to decide on the row-wise or the column-wise and build a loop even to allocate. That is not necessary here. All right. So then we build it. That will compile the pyx code, so that will define a new module that we then can call. Here is the timing. So this is the run game better module that was compiled, and that is here imported. We import the update function. So as we do the update, also automatically we get the neighbors that are being called from this compiled function. So it's important each step we actually call the compiled code. All right, so the code without the animation runs more than 4 times faster. So, and the main loop is still not optimized. So there are still better things that can be done. One can also add typing to the main loop. So the main loop is actually also running in an interpreted manner. So it could also be better. All right, visualization with matplotlib. So we run the same setup, but now the imports are different. This is an interactive update. So there's also, we've seen how to work directly with the Kinter module, so which is very nice to learn about object-oriented programming again. If you're only interested in animations, then the Kinter canvas can be a little bit overkill. So we can work with the visualization of sparse matrices. I think I suggested that also in lecture 4. So the plot is then done in just a couple of instructions. If you have ever used MATLAB, it's very similar syntax. So we are using blue dots here for indicating every living cell. The matrix is converted into a sparse matrix. So there are still in this animation a lot of improvements to be made here. But it is an animation, so this is meant for output. I'm not entirely sure if there's so much to optimize here, because we need to wait always a little bit for the user to notice. Okay, we run this 1000 because 1000 was the dimension was 200, and then we draw this. Here is the timing with the wall clock time. So I ran this on the MacBook, not on the Windows here, but you can see it runs more than twice faster. We also observed this during the live run in this lecture. So this makes it run twice faster. Okay, so we can improve the running time a lot. So my time is about up. So just to mention something, another tool, Numba. So Numba can be seen as a package that uses Cython and NumPy. So it's a bigger scope as well. So it works also via the compilation, but it also is geared towards multi-threading and GPU acceleration. So we ended a week on parallel programming. It's another way, and perhaps a better way, or certainly to do a better way than using the threading that is built into Python. So if you have to do multi-threading, then that would be the recommended tool to use from within Python. And it also supports GPU acceleration. Okay, and then it helps you to compile, and the code then again runs at native code. So it works with Cython. It's most likely if you install Numba that you get Cython for free as well. So I have not much experience with this, so this was copied from the 5 minutes Numba, and I give this to you here in about 2 minutes. Okay. But I hope that this lecture was interesting. It shows that the disadvantage of Python being slow is actually not entirely fair if you use the ecosystem of Python well. So, which means that every Python programmer knows vectorization. Scientific Python programmer knows scientific knows NumPy, knows thus vectorization. This is an additional tool. Compared to vectorization, you keep the same logic. We get the performance close to native C code without having to go into C. Although, I mean, there's never any harm of getting to learn some C in this way. Okay, the exercises are kind of open-ended here a little bit, except the second exercise, which is then also harder because we left the vectorized code of lecture 4 as an exercise. So what do you expect to be better? either the vectorized code of lecture 4 or the C code. I can perhaps already give you some um, suspicion. So here in this code, we still create each time an entire new numpy matrix. This might be quite bad. So there is also some. It's only a 200 by 200 matrix, but still. So the other way would be, so the improvement, so the main improvement in exercise 3 would then to avoid doing that extra allocation of the new matrix. So simply work with a pair of matrices where you have the previous and the current and simply each time swap the two. Okay, so the composite integral was with the square root, but what if you have to do this for any function? Can you also give any C library function to that? So that makes it rather flexible. So you then mimic a little bit the code generation, what is also the just-in-time compilation. That is done from within Julia. So in some sense, Julia claims to do a lot new stuff, and it's indeed one feature. But the Python scientific programmer can actually also already do this. Okay, thank you for listening. I hope this was interesting.